In previous video, we started the discussion of continuous random variables using the example of a spinner. There we demonstrate that for a continuous random variable, the probability that x equals any possible value in its support is in fact 0. That means we cannot use a probability mass function or a two-way table or a probability distribution table to describe the distribution of a continuous random variable. Instead, we defined a new concept, the cumulative distribution function, or CDF. The CDF of the random variable is a function that maps the real line to the 0-1 interval, 0 to 1 interval. The CDF is defined to be probability that x is less than or equal to little x, where little x is a value in the real line. The cumulative distribution function can describe the whole distribution of the continuous random variable. We mentioned that CDF can be used for both discrete and continuous random variables. For discrete random variables, cumulative distribution function is a step function. And for continuous random variables, the cumulative distribution function is a continuous function. The cumulative distribution function, by definition, has the following features. The first feature is that the CDF is weakly increasing. This is easy to see from the definition because when you increase this upper bound, little x for this inequality, then that makes this event more likely. It's more likely for x to be less than or equal to 3 than for x to be less than or equal to 2. So whenever you increase this little x value, this event becomes more likely, that has higher probability. So CDF is weakly increasing. And when you take x to minus infinity, the CDF evaluated at this along this sequence converges to 0. So that's also easy to understand. When you take this upper bound little x to infinity, makes it as negative as possible, then this event becomes as close to an empty event as possible. An empty event has 0 probability. And when you take little x to positive infinity, the CDF approaches 1. That's simply because when you take this little x to positive infinity, this inequality becomes more and more likely to be satisfied for all values of x. That's this event gets closer and closer to the universal set, and therefore the probability approaches 1. For continuous random variables, if the CDF is also differentiable almost everywhere, then we can define another representation of the distribution for the random variable. That's the probability density function. The probability density function is defined to be the derivative of the CDF. Conversely, we can also obtain the CDF from the PDF. The CDF can be obtained from the probability density function by taking an integral. Integral of the PDF function, where the integral range is from -infinity to little x. So this follows from the relationship between derivative and integral. By definition, the probability density function also has some features. A probability density function cannot be negative. So it cannot be negative. This is simply because it is the first derivative of a weakly increasing function. And also, when you integrate the PDF up over the whole real line from -infinity to +infinity, you get the limit of the CDF as you take little x to infinity, and this follows from this relationship. And that we already know is 1. So a PDF function integrates up to 1. For discrete random variables, we defined the expectation of the random variable as the weighted average of the possible values, where the weight is given by the probability mass function. For continuous random variables, the idea of the definition is the same, but instead of using summation to define expectation, we now need to use integral. Integral of x PDF x dx. This is analogous to the discrete case. So remember that in the discrete case, expected value of x equals summation x in the support of x times the probability mass function. Notice that even though we use the same notation for probability density function and probability mass function, they are defined differently. This is the probability mass function. And it equals probability that x equals little x in the discrete case. So as you can see, these two definitions are quite analogous. The only difference is that in the discrete case, we are able to sum over all the possible values because there are only finite or countably infinite number of them. Well, in the continuous case, we are using integral because the number of possible values is uncountably infinite. That's the definition of expectation for continuous random variables. We can also define the variance of the random variable in a similar way. The variance is still, just like in the discrete case, is the expected value of the square of the deviation of x from its expectation. And except in the continuous case, these two expectations are expressed in terms of integrals. Are expressed as integrals with the weight given by the probability density function. Now let's consider an example this example actually comes from the spinner example we talked about before. In a fair spinner example, when we spin the hand of the spinner, the number that the hand lands on is the random variable x, and that random variable x follows this distribution, follows the distribution given by this probability density function. We drew the graph of this probability density function. So that is 0 and that is 1. And this probability density function is flat on the 0, 1 interval, flat at 1 and 0 elsewhere. And according to the interpretation of probability density function, this means that the probability that the hand of the spinner lands in any small interval is the same. So the probability that it lands in the vicinity of any point is the same. So whether it's here or here, the probability is the same as long as this interval we consider have the same length. So that's what a fair spinner means. So now with this probability density function, we can calculate the expected value of x. The expected value is the integral from -infinity to infinity, little x, probability density function of x dx. But note that the probability density function equals 0 unless little x is on the 0, 1 interval, 0 to 1 interval. Therefore, we only need to consider this interval. So on this interval, the probability density function equals 1. So the integrand is x times 1 dx. And that gives us 1/2. So the expected value of x is 1/2 in this example. The variance of x can be calculated in a similar way. Again, we can take the integral of little x minus the expected value of x, which is 1/2 squared times 1 dx. And that should be 1/3 x minus 1/2 to the power 3, evaluated on 0 and 1. And that gives us 1/3 times 1/8 plus 1/3 minus, it's plus because it's to the power 3. So 0 minus 1/2 is minus 1/2 to the power 3 is minus 1/8. It's plus 1/3 times 1/8 equals 1/12. Another concept that can be very useful for continuous random variables is quantiles. Quantiles can be defined for discrete and continuous random variables, but it's mostly it's more useful for continuous random variables. So what are quantiles? Quantiles are inverse of CDF. So quantile function is an inverse function of the cumulative distribution function. So the cumulative distribution function is a function that maps from the real line to 0 to 1 interval. The quantile is the inverse of that. The quantile function maps from 0, 1 to R. In fact, usually we don't take the closed interval, we take the open interval 0, 1 to R. The quantile function is the inverse function. It's defined on this open 0 to 1 interval, and it maps 0 to 1 interval to R. And how is it defined? Well, if fx is strictly increasing on the whole real line, then the definition of quantile is very easy to do. It can simply be the inverse function of that strictly increasing CDF. It's a little bit tricky when the CDF is not strictly increasing on the whole real line, which is actually a typical case. In that case, we need to adjust the definition of the inverse function a little bit. So the quantile function, add the value tau for tau in the open 0 to 1 interval is the smallest x value such that CDF evaluated at this point is greater than or equal to tau. So this is the definition of the quantile function. So for tau in the open 0 to 1 interval, the quantile of x at tau is the smallest x value such that the CDF at little x is greater than or equal to tau. Well, so this is actually stating the same thing for a tau in 0, 1, the inverse, the quantile function is the smallest x such that fx is greater than or equal to tau. Now we consider an example just to illustrate how we find that inverse function. This example is maybe too simple. In this example, this is actually the CDF for the outcome of the spinner, of the fair spinner. So this CDF function, there are two segments. The CDF equals little x for little x on the 0 to 1 interval, and equals 0 for x negative, and equals 1 for x greater than 1. So if we draw it on the graph, it looks like this. It's 0 for all the 0 or negative x, and it's 1 when x is greater than 1. And on the 0 to 1 interval, it is this 45-degree line. So this is the CDF we are considering. It is weakly increasing. It's strictly increasing on the 0, 1 interval, but flat elsewhere. So when you define the quantile function for this distribution, we first note that on the 0 to 1 interval, when tau is between 0 and 1 on this open interval, that is, we take any value of the probability on this open interval. Say here, we see that the CDF It's gonna map the only point of x that maps to this point on this 0 to 1 interval is equal to that point, because the CDF on this interval is the 45-degree line. So suppose this is tau, then this should equal to tau, because that line is the 45-degree line. And therefore we can draw on this right-hand side. Suppose this is tau, and for any tau on the 0, 1 open interval, we find the quantile equals tau. So that's the 45-degree line on the 0 to 1 open interval. And that's enough because we only define the quantile function on the open 0 to 1 interval. So that is the quantile function of this distribution. There are some concepts that are related to quantile. These are actually special cases of quantile. The first, maybe the mostly used concept is median. The median of a random variable x is in fact the quantile at 50% or at 0.5. It is called the median because this value is supposed to be right in the middle of the distribution. So there are half of the states, in half of the states, the random variable is greater than this median. And in half of the states, the random variable is less than this median. So this holds for continuous random variables. So median can be defined for discrete random variables, but for discrete random variables, this does not hold. Only for continuous random variables, these hold. The reason is that for continuous random variables, probability x equals median equals 0. Well, for discrete random variables, this typically is not true. So median is the 50% quantile. And another related concept is percentile. Actually, I want to ease you into percentile. Let's talk about quartile first. Quartile. Notice that this word quartile is not the same as the word quantile. So quantile is this word. So these two words are different. This is quantile and this is quartile. So what is quartile? Quartiles, in fact, there are 3 quartiles. The 3 quartiles are the 20% quantile, 25% quantile, and the median, which is the 50% quantile, and the 75% quantile. So these 3 points are kind of special. They kind of are evenly distributed. They split the population into 4 equal probability parts. So in the example that we just considered, where the quantile function is this 45-degree line on the 0-1 interval. The quartiles are the median, the 25%, and the 75% interval in quantiles. So this is the first quartile, and the second quartile, and this is the third quartile. So there are 3 of them. Quartiles split the support of random variable x into 4 parts, and the random variable belonging to each of the 4 parts, the probability that the random variable belonging to each of the 4 parts is the same and equals 25%, 1/4. And that's also why these special quantiles are called quartile, because quar means quarter, and that means 1/4. So that's the definition of quartiles. And quartiles are important and useful when we want to measure inequalities. For example, if X is income, then when income is equal across people, when X is evenly distributed across the whole population, when everybody earn about the same income, then the different quantiles will be similar. So the difference between the 25th quantile and the 75th quantile, so the low income people and the high income people would be earning about the same. So the difference between these two will be small. Well, on the other hand, if income is unevenly distributed, the rich are much richer than the poor, then the difference between this 25 quartile, the first quartile and the third quartile will be different, will be very different. So there is this concept of inter-quartile range. It equals the third quartile, which is the 70% quantile, and the first quartile, which is the 25% quantile. And that provides one measure. This is not the only measure, but it's one of the measures of inequality. Also recall that in discrete random variable case, we defined conditional distributions of one variable given the value of another random variable. We defined the conditional distribution of y given x equals little x. So that is our assessment of the distribution of y after the value of x is reviewed to be little x. In the discrete case, the conditional distribution of y given x equals little x is given, can be derived very easily or follows directly from the conditional probability formula. So in the discrete case, we had the probability mass function of y given x for x equals little x is given by the joint probability mass function of the two divided by the probability mass function of the conditioning variable x evaluated at little x. So that's the formula we had for the discrete case. This f is the probability mass function. So the f's are probability mass functions in the discrete case. Now, that is the case. So that is how we define the conditional distribution when both x and y are discrete random variable. Now we have introduced the continuous random variables. We have now a few different cases. The first case is when y is continuous, well, x is discrete. When y is continuous and x is discrete, we can define the conditional CDF of y given x equals little x using the conditional probability formula. So that should be probability that y is less than or equal to little y given x equals little x. So this is the event A and this is the event B. So that's PA given PA given B. PA given B by the conditional probability formula is probability that A and B divided by the probability of B. So that's how you may define the conditional CDF of y given x when x is discrete. The fact that x is discrete is important for this definition because otherwise the denominator would be 0. If x is continuous, this would be 0. Well, if x is discrete, the denominator is positive, then we are able to define the conditional CDF in this way, using this formula. And in order to obtain probability density function, conditional probability density function, we simply take the derivative of the CDF. Because now we are considering the CDF of y, we take the derivative with respect to y. And the second case is when y is continuous and x is also continuous. And now you see we ran into some problem. We cannot use this formula anymore because for continuous random variables, probability that x equals little x equals 0. Then how do we define the conditional CDF of y given x equals little x? How do we even define this? It cannot be probability that y less than or equal to y given x equals little x because this later quantity, this is not well defined because the conditioning event has 0 probability. Then how do we define it? What's our solution to this problem? The solution is to consider not only the probability that x equals this little x point, but also the probability that x is in a small neighborhood around this point, in a small interval around this point. So it's the conditional probability of y less than or equal to little y, conditional on x lying between little x minus epsilon for some epsilon that is positive, so for some positive number. But you might ask, what positive number? How large do I make this positive number? Well, in fact, you do not have to choose. We can take a limit and drive this positive number to 0. And that is the definition of conditional CDF when both y and x are continuous. This, in fact, also applies when x is discrete and, when y is discrete and x is continuous. So this also applies when y is discrete and x is continuous. And you can take a derivative of that to obtain the PDF. When both y and x are continuous, when both have probability density functions, it turns out that this definition implies the probability density function. So this definition implies that the probability density function, conditional probability density function, is in fact of the same form as in a discrete case, where this joint probability density function is the cross derivative of the joint probability, joint CDF of the two random variables. And the joint CDF, it might not surprise you, is the probability that x is less than or equal to little x and y is less than or equal to little y. So this is how conditional probability density function can be obtained from the joint and the marginal density function of the random variables. Now let's consider an example, one example where x is continuous and y is continuous and x is discrete. In this example, y is years lived after tumor removal for a kind of tumor. And suppose the years can be measured in fractions of years. So y is a continuous random variable. And x is a discrete random variable. X takes two values. One is if the tumor was cancer, was malign, or 0 otherwise. So you may find the conditional distribution of y given that x equals 1. So this is y. Given that x equals 1, by looking at the population of patients who had malign tumor and assess the distribution of their years lived after surgery. And you may find that this distribution is something like this, something denoted by this. So suppose that is the distribution that you find. And you can study the other patients, the patients who had benign tumors, and look at their years lived after surgery, and you denote their distribution by this, by PDF y given x, little y given 0, given x equals 0. And those distributions may also be expressed in terms of CDFs. So these are the distributions, PDF and CDF, for the people who had malign tumor, had x equals 1. Well, these are the distribution, PDF and CDF, for the patients who had benign tumor. Now, the overall distribution of years lived across all patients can be obtained from these conditional distributions. Let's consider the CDF. The CDF equals probability that y is less than or equal to little y. And by the law of total probability, that equals probability that y less than or equal to y and x equals 1 plus probability that y less than or equal to little y, x equals 0. And that is equal to the conditional probability of y less than or equal to little y given x equals 1 times probability that x equals little 1 plus probability that y less than or equal to little y given x equals 0 times probability x equals 0. So this equation follows from the law of total probabilities. But notice from the definition of conditional CDF, this is the conditional CDF of y given x equals 1. So that is fy vertical line x parenthesis little y given 1 times probability that x equals 1, which is the probability mass function of x evaluated at 1. Similarly, here, this is the CDF of y given x equals 0 times the PMF of x at 0. So this is how the unconditional distribution of y and the conditional distribution of y given x are related. And in fact, as you can see, if you take a first derivative with respect to y on both sides, you find that the PDFs, the unconditional PDF and the conditional PDFs are also related in the same way. So the unconditional distribution is a weighted average of the conditional distribution. So in the discrete case, this weighted average is expressed in terms of summation. Now that we have conditional distribution defined, we can define conditional expectation. Just like expectation is a summary quantity of the distribution, conditional expectation is also a summary of the conditional distribution. So for continuous random variables, if y is a continuous random variable, The conditional distribution of y given x equals little x can be found by taking this integral over the whole real line, y times the conditional probability density function of y given x dy. So that's the definition of conditional expectation. For continuous random variables, just like in the discrete case, we have a way to view conditional expectation as a random variable. The thought experiment goes as follows. We first realize that EY given x equals little x, this is a function of little x. The value of this quantity varies with x and only varies with x, So we can define mx, we can let that function be denoted by little mx. So little mx is the notation we give for this function of x. So this is a function of x, and we denote that by little mx. Then little m is a function. We can plug in the random variable x into that function. Then that little m capital X, that is a transformation of random variable x. And therefore itself is also a random variable. And that random variable, conventionally, we use this notation to denote. We use this notation, EY given x without the equal little x sign. We use this notation to denote this random variable. And that's how we understand this notation to be a random variable. That is, it is a transformation of x. And since it is a random variable, it possesses expectations, it possesses distribution, it also has expectations. So we can take an expectation of this random variable. Expectation of this random variable. Now, if you still find this notation confusing, you can go back to little m. Just remember what little m is. You can go back to this notation. And how do you find the expectation of this transformation of x? We can take an integral of little m x density of x dx. So this is when x is a continuous random variable. If x is a discrete random variable, you can use the summation instead of integral. And that equals, remember what little mx is. Little mx is here. So little mx is itself an integral. We plug that integral into this integral, and we find that is integral y conditional density of y given x equal little x dy marginal density of x dx. Now, if we put the integrand functions together into this double integral, we find that equals the double integral y times the conditional density times the marginal density dy dx. Just recall that we have mentioned or derived, we didn't go through the whole derivation process, but we claimed that the conditional probability density function equals the ratio of the joint and the marginal of the conditioning variable. Therefore, the product of the conditional and the marginal, product of the two, equals the joint. So the product of these two equals the joint probability density function. Dy dx, and that's exactly the expected value of y. So what we have shown is the iterated expectation equals taking the expectation once. What we have shown is this equality. So that is the law of iterated expectation. It holds for discrete and holds for continuous random variables. It holds for all cases. It holds for the case where y is continuous, x is discrete, and also when y is discrete and x is continuous, and also when both are continuous and both are discrete. So we don't do the derivation of all of them, but we should understand that the law of iterated expectation applies in all of these cases. Now that's conditional expectation. You could also define conditional variance. The conditional variance in the continuous random variable case equals, again, it is the expected value of the difference between y and its mean, but because we are considering conditional variance, the mean or the expectation is the conditional expectation. So let's actually start with the conditional variance evaluated at a point. Conditional variance of y given x equals a particular value of x. Squared, so the deviation of y from its expectation squared, and then we take the conditional expectation of x equals little x. So this conditioning event is associated with this expectation sign. So these two are a system. And this conditioning event is associated with this expectation sign. These two are a system. They always come together. And you can write this outer conditional expectation in terms of integrals, in terms of an integral. So that is the definition of conditional variance. Again, you can define a notation for conditional variance, define the random variable notation for the conditional variance in the same way as you define EY given X. So you can let Vx denote the function variance of y given x equals little x. We can define this function because this conditional variance is a function of little x. then realize that V of capital X is a transformation of X. And therefore, it is a random variable. And then we can let the notation variance of Y given capital X to denote this little v evaluated as the random variable. And this is the sense in which we view conditional variance also as a random variable. It is a transformation of X. So for the continuous random variable case, it is just like in the discrete random variable case, we had this, we still have this decomposition of variance. I'll just restate the decomposition of variance without deriving it. The derivation is actually the same as in the discrete case. The variance of Y can be decomposed into this within group variance, the average within group variance, and the across group variance. For the discrete random variables, we define the independence of two or more random variables. For the continuous random variable case, we can do the same thing. X and Y random variables are independent if the conditional distribution equals the unconditional distribution. Or in other words, if both are continuous, the joint distribution, the joint probability density function, equals the product of the marginal probability density functions. So two random variables are independent if the probability density function satisfies the product rule. Or equivalently, you can also use joint cumulative distribution functions. The joint cumulative distribution function should also satisfy the product rule. All these statements are in fact equivalent. You can claim independence whenever each one of these hold, and these statements also imply each other. So you can define independence in this way. Now let's consider one last example for this video. In this example, we spin two spinners, spinner 1 and spinner 2. We spin both spinners and record the outcome. Let the outcome of the first spinner be X and the outcome of the second spinner be Y. Let both be fair spinners, and also let the outcome of the spinners be independent. So let spinners be fair and the two be independent. Now consider a new random variable Z. This new random variable z is the maximum value of x and y. So maximum of x and y. Now, what is the probability density function of z? Well, from previous discussion, we have learned that if the spinors are fair, then the density of y and x are the same, and they are both equal 1 when the value is on 0, 1 interval and 0 elsewhere. And because they are independent, so the joint equals the product. Now, how do we find the probability density function of the maximum? We can start with the cumulative distribution function. The cumulative, so we can start the derivation from the cumulative distribution function. So fz of little z. Fz of little z is probability that z is less than or equal to little z. And probability that z is less than or equal to little z is equivalent to the maximum of x and y being less than or equal to little z. And the event that the maximum is less than or equal to little z is equivalent to both are less than or equal to little z. If both are less than or equal to little z, then the maximum is less than or equal to little z, and vice versa. So therefore, that equals the maximum, that equals the joint probability of these two events. Oh, this is actually the joint CDF of the two events. It's actually the joint CDF evaluated at the ZZ point. Now, due to independence, the joint CDF equals the product of the marginal CDFs. So this is by independence. And the marginal PDFs is related to the CDF. Marginal CDF is related to the PDFs in the following way. So it's the integral from minus infinity to z PDF dx times minus infinity to z PDF of y dy. For that, as we can see, if little z is between 0 and 1, so that equals, so now we can discuss if let's because we don't have a lot to say, we can make this smaller and make some space. Now, these two integrals, we can work on these two integrals. And because we know x and y have the same distribution, these two integrals should have the same value. So let's now just work on one of them. So let's work on one of them. The integral from infinity to z, fx dx, that function, we know it equals 0 if z is less than or equal to 0. And we also know it's 1 if little z is greater than or equal to 1. For z is between 0 and 1, we need to do this integral, and that integral should be the integral from 0 to z, fx little x dx. And between 0 and 1, the density is in fact 1. Because fx equals 1 when little x is between 0 and 1. So therefore, that integral equals 0 if z is less than or equal to 0, and 1 if z is greater than or equal to 1. N is the value of this integral, and that integral equals z. And therefore, so this quantity equals 0 if z is less than or equal to 0, and z squared because we got z here and also z here. So therefore, that's z squared if z is between 0 and 1, and 1 otherwise. Now that is the that is the CDF of z. In order to get the PDF, we simply take the derivative. The derivative of that is 2z if z is between 0 and 1, and 0 otherwise. So that is the probability density function for the maximum of the two outcomes from the spinors. So here we have used independence, and this is one of the ways independence can be very useful in our derivation.